All right. I hope it's clear. Yeah. Next is least integer function. This is also piecewise continuous. And how do you get least integer function? You look at the look at the what charges. Let's say you have to pay for the vehicle. So if you are paying, if your vehicle is there for 2 hours 5 minutes, you have to pay for 3 hours. Okay, so if it is there for 2 hours 55 minutes, even then you have to pay for 3 hours. And even if it is 2 hours 5 minutes, even then you have to pay for 3 hours. So meaning is it is the least integer function. Okay, all right. So here is sine 1 by x, and this is the most important function, that is so called the Gaussian, and e to the power minus x square. All the lifespan of these lights and so on, all these follow through the e to the life. Our life also follow according to this function. You are at the middle, you are at the top when you are at the middle. Okay, so when you think you are at the top, so you are almost at the middle of your life, and then suddenly it goes down and reaches to 0. Okay, so let's try to have a formal definition. Given epsilon greater than 0, there is a delta such that modulus of x minus x naught is less than delta, implies fx minus fx naught is less than epsilon. Or equivalently, you have, this is so called the sequential continuity, but it is same in the case of the R, that is limit of f of xn is equal to f of x naught, where xn is a sequence converging to the point x naught. This is more easy to use, and it's difficult to use, but it is important because I'm going to talk about uniform continuity. So from here I will be able to get to that. Okay. So here, if you look at these figures, this is the variation of your x. So x varies from a minus delta to a plus delta, and fx varies from f of a minus epsilon to f of a plus epsilon. And that is, if you change, you have correspondingly change in fa. So let us try to see it for a simple function. If you look at ax plus b, you can take your delta to be epsilon upon mod a. That is an easier thing. So don't, this is simple, but as the functions get complicated, it's a difficult job to compute delta. It's not easy. Don't ask, just don't give arbitrary function to your teacher and ask him to get the delta. That is it. Not so. I can show you how this is. Say fx is 3x squared plus 2, and so compute fx minus fx naught, so you get this. So what I have to do is to bound this x plus x naught. Whenever x is close to x naught, this should be somehow bounded, so it should not depend on x. Okay, and that we can do. Let us restrict ourselves to the disk, to the open disk. X minus x naught less than 1, so mod x will be less than 1 plus mod x naught, and x plus x naught will be less than 1 plus 2x mod x. So 1 is there and 1 plus 2x naught. So let us take the minimum of the two. So take delta to be 1 upon 3 2x naught plus 1. So this delta will serve the purpose. So that is how in the, but there is a point Why I have done this? Because this delta somehow is depending on the point x naught. That is to be. Okay. Similarly, you have x square sine 1 by x, take delta to be root epsilon, that is simple. So this is x square sine 1 by x. It is lying between the two parabolas. So here function looks like this. Similarly, you have how to do it is not continuous. You create a sequence such that f of xn does not converge to the same f of x naught. So I have created one sequence xn. It is 1 upon under root of 2n pi plus pi by 2. And if you put the values over here, this xn goes to 0 and f of xn goes to 1 upon xn. So it goes to infinity, meaning is this is not a continuous function. Same situation here graphically, 1 upon x sine 1 by sine x square. So we begin with a try to analyze the continuous functions. So here is a real valued function on R and nowhere continuous. Okay, defined on whole of R but nowhere continuous. So you take 1 if x is a rational number, it is 0 if x is not a rational number. So we can draw it, and but then it looks like this. Okay. No. How can we prove that this is not continuous at all? You create, let us take say point half and approach half through rationals and approach half through irrationals. So if I approach through the rationals, say that it is 1 by 2, 1 by n, xn goes to 1 by n, 1 by 2, and yn goes to 1 by 2 again. So you have x, but g of xn is 1 and g of yn is 0, implies limit of g of xn is not equal to limit of g of yn, means this limit does not exist, so no question of continuity. Next is fx is exactly continuous at only one point, that is at 0, and so discontinuous everywhere. And this can be done again same way. We construct a sequence of rational number converging to C and yn of irrational numbers converging to C, and you get this limit as C and this limit as 0. So f is not continuous at any point which is not 0, and it at continuous at 0 is clear. Now, one point can be extended to finitely many. So here the continuity at finitely many point and discontinuous everywhere. Next is continuous only at rational points. So this you might have studied. So it is this function 1 at if x is 0, it is 1 upon n if it is a rational number non-zero, and it is 0 if x is not, if x is an irrational number. So in this case f fails to be continuous at every rational points, and f is continuous fails to be continuous at every rational point and continuous at every irrational point. So natural question is there is an example of a function with the opposite property? That is, does there exist a function on R that is continuous on Q but fails to be continuous on irrationals? And unfortunately, the answer is no such function exists. And this can be done little bit of mathematics, but I have just written down few major points to how to show that there does not exist any such function. You define so-called F sigma set, that is the union of arbitrary countable union of closed sets. So every open interval is already a F sigma set. Every closed set, every closed interval is also a F sigma set, and every open interval is also a F sigma set. and then you prove that the set of discontinuities of any function is F sigma set, and the set of irrational number is not an F sigma set. So meaning is that there is no such function with this property. It remained quite an open question for quite some time, but now we know this very well. Similar, this is a simple thing. We can generate, you know all these. I have little less time. So I can generate now with those things, addition and scalar multiplication and composition. I can create many more continuous functions. Right. And this is simple property that if it is a bounded set, a bounded function, and if these are simple properties of continuous functions which I can avoid. F assumes if it is on a closed interval, then it assumes its maximum and minimum values. And you are well known to intermediate value theorem, and these are just, I can avoid it. Now I come to the uniform continuity. So how come this? Look at 4x plus 1, we remember I can take delta to be epsilon by 4. So this is fine, it does not depend on any point. And let us use, instead of 3x square plus 1, I am just using x square, and delta will be epsilon upon twice c plus 1. Means larger value of c gives me smaller value of delta. So as c becomes larger and larger, delta will become smaller and smaller. Say epsilon is 1, delta is 1 by 3, sufficient for c is equal to 1. However, if c is 10, delta will be 1 by 21 is required. So meaning is we are not comfortable. I mean, my delta is continuously depending on the point c. That is graphical representation. This is fx is equal to x square, and you can see this range is becoming smaller and smaller as we go towards the right. That is what is happening over there. So a function is uniformly continuous on A if for each epsilon greater than 0 there is a delta such that modulus of x minus y less than delta implies fx minus fy is less than epsilon. So continuity is a local phenomena, and uniform continuity is a global phenomena. Okay, something like if you look at the elections, your election for the metropolitan is a local phenomena, and local issues are involved. Whereas if there is an election for MP, there are global issues are involved. So it is just the same kind of concept over here. Uniform continuity is a global phenomena of continuity, and continuity is local phenomena at the point x naught. So a function fails to be uniformly continuous. It is a difficult job to say that it does not depend on the point x. So how to show that some function is not uniformly continuous? You create two sequences xn and yn such that xn minus yn goes to 0, and f of xn minus f of yn is little bigger than a given number. So let's look at sine 1 by x. So I have chosen two sequences. Xn, say epsilon naught is 2, and xn is 1 upon pi by 2 plus 2n pi. Yn is 1 upon 3 pi by 2 plus 2n pi. So one is the odd one is the even. So both x and yn goes to 0. So xn minus yn goes to 0. But f of xn is 1, f of yn is minus 1. So the sum, if you subtract them, it is 2. So this meaning is this is continuous at every point of the open interval 0, 1, but not uniformly continuous. Say fx is x square, graphically we have seen it, but analytically you can see xn take xn to be n, yn to be n plus 1 by n, xn minus yn goes to 0, and f of xn minus f of yn can be made more than or equal to 2. So epsilon naught is 2 here, and meaning is this function is not uniformly continuous. So with the help of this criteria, we can, of course, if a continuous function on a compact set is uniformly continuous. Next is uniformly continuous on the real line. We are talking about closed interval, but if the function is continuous and vanishes at infinity. So here is, that's why I showed you Gaussian earlier. And the Gaussian and the function here is e to the power minus mod x. Both of them are vanishing at infinity. And if a function is continuous on R and vanishes at infinity and minus infinity, then the function is going to be uniformly continuous. Similar, continuous bounded function need not be uniformly continuous. Say sine of 1 by x square. Sine of 1 by x square is a bounded continuous function, but it is not uniformly continuous. So on the open interval, it is a simple job. F is uniformly continuous on the open interval if and only if both the limits exist. That is simple. Product, yeah, that is a difference. Product of two continuous function, pointwise product, is a continuous function. But the product of two uniformly continuous function need not be uniformly continuous. That is, for example, fx is x and sine x. So product is not uniformly continuous, whereas both of them are. Say, how can we say a little bit? This you might have done in the class, that if f is uniformly continuous, then it sends a Cauchy sequence into a Cauchy sequence. So how can we use this? Say 1 by x square is not uniformly continuous on 0, 1. You look at the sequence 1 by n, its image is n square, which is not a Cauchy sequence. So meaning is it's not, this criteria is not satisfied, so f is not uniformly continuous on the open interval 0, 1. Till now, I have finite intervals, right? So this is a summary. If f is another condition, so we have to find, there is no if and only if condition with us which can say that every continuous function is going to be uniformly continuous. So we have to find out some sufficient conditions. So there are, this is always a challenge. Even you can publish this even now, that find a sufficient condition which, under which the given function, continuous function is uniformly continuous. Okay. So here is a continuous function satisfying Lipschitz condition, and then if Lipschitz conditions are satisfied, then f is uniformly continuous. So for example, 3x plus 7, x square, 1 by x square, and so on. So this is just the summary of what I have just done. So if f is Lipschitz condition, then f is uniformly continuous. If the limit is a real number, even if it exists at infinity, then that is also uniformly continuous. On R, both the limits are 0, then f is uniformly continuous. If f is continuous and periodic, then it is uniformly continuous. Monotone bounded is uniformly continuous. And if such a relation is satisfied, then again we get the uniform continuity. So here is a criteria to see, as you have for the series, we have a criteria like this. Most of these criteria you won't find in the books. but you have to look for some research papers. So first one here is from a infinity to r be a continuous function. If the limit is 0, then f is continuous if and only if g is, sorry, f is uniformly continuous if and only if g is uniformly continuous. So how to use it? That is like this. You have a function root x uniformly continuous on 1 to infinity. I have another function fx sine x cube upon x root x. So if you take the subtraction and extending to infinity, this will the subtraction will go towards 0, and meaning is f and g are uniformly continuous simultaneously. So f, I know that g is uniformly continuous, so f is uniformly continuous. So this example is particularly interesting because f does not have a finite limit at infinity, and neither it satisfies the Lipschitz condition. So those summary things are not satisfied, but still we can conclude that this is a uniformly continuous function. Okay, next is say gx is x square is not uniformly continuous. So you look at sine x square upon x, and x square is, so you take the difference and the difference goes to 0, and therefore both of them should be uniformly continuous at the same point, but I know g is not uniformly continuous, so f is not uniformly continuous using the same. This is a well-known thing. If f is limit exists and it is there is an oblique asymptote at infinity, then the function is going to be uniformly continuous. Next is if it's dominated by the line, then it is uniformly continuous. So modulus of fx is c1 times x, then the function is going to be uniformly continuous. Mind it, these are infinite intervals. All these results, we do uniform continuity on the finite intervals. This is, I'm talking about all infinite intervals. So if limit is upon x is infinity, then f is not uniformly continuous. So we have x to the power alpha, alpha less than or equal to 1 is uniformly continuous on a to infinity, and moreover g is uniformly continuous on 0 to infinity if and only if alpha lies between 0 and 1. And log x is uniformly continuous on a to infinity for any a greater than 0, but if you include 0, it is not uniformly continuous. Similarly, your e to the power x is not uniformly continuous, whereas the Gaussian e to the power minus x square is uniformly continuous. Here is another criteria. So f is a continuous function on a to infinity and derivable, and the derivative limit exists. Then the necessary sufficient condition for f to be uniformly continuous is that this limit should be finite. This limit should be a is finite. Say you have comparison test kind of thing available. If f and g are derivable on I and g dash x is less than L times modulus of f dash x, then f is uniformly continuous on I implies g is uniformly continuous on I. So if the upper one is uniformly continuous, lower is also uniformly continuous. So we can generate some comparison tests. Say for example, how can I apply it? Say g fx is root x is uniformly continuous on 1 to infinity. Take gx as sine root x. So you take the differential, and the differential is less than this, that is less than, so it is less than 1 by this g dash x is less than f dash x, meaning is this g is also uniformly continuous. F is known to be uniformly continuous, and I can conclude that sine root x on 1 to infinity is uniformly continuous. Here is another result, as you have result for the infinite series. So infinite series, we have f and g be continuous on a to infinity and derivable on a to infinity, and if the limit of derivatives is equal to L, if L is between 0 and infinity, then f and g uniformly continuous together. If L is 0, meaning is g implies f, and if L is infinity, then g not uniformly continuous implies f is not uniformly continuous. Say I have fx is equal to log x plus root x. This seems to be a difficult function, but then we can manage it. X belonging to 1 to infinity, take gx is equal to log x. Log x is uniformly continuous. Take the derivative and the limit is 1. So it says g is uniformly continuous, so f is also uniformly continuous. Okay, so from R I can move to Rn. Okay, those who are in second year or third year, they can understand. From Rn to R is uniformly continuous if you have d of xy, the length distance between x and y is less than delta, implies fx minus fy is less than epsilon. Only difference is that x and y distance is required instead of the modulus. Modulus was distance on the real line, and here the distance is the Euclidean distance. And here it looks like, here is Rn to R, fx is equal to mod x is uniformly continuous. So take delta equal to epsilon, and this function looks like this nice function. Similarly, if you have f of x plus y is x plus y, so that is the plane. So this is uniformly continuous on R2. We have a similar criteria that how to see uniformly continuous. Here is uniformly continuous on D if the set is closed and bounded, then every continuous function is uniformly continuous. But if here D is uniformly continuous on D, how to find out? You find out two sequences x and yn, u and yn, such that their Euclidean distance is going to 0 and the images must go to 0. So if you have to prove something is not uniformly continuous, generate these sequences so that the images don't go to 0. Similarly, we have the restrictions are going to be uniformly continuous. So here is an example. Say fx d is all xy such that xy belongs to 0, 1, and so it is the rectangle minus the point 0, 1. Okay, rectangle 0, 1, 0, 1, point, leave behind the point 1. So say function is f of x plus y. So f is continuous on D but not uniformly continuous. How to see it? You consider the sequence xn, yn equal to 1 by n 0 and un vn as 1 upon n plus 1, 0. So this goes to difference, Euclidean distance goes to 0, but their difference of the images does not go to 0. So meaning is this is not uniformly continuous. Keep in mind D is bounded but not closed. So similarly, if you have a x square plus y square, f is continuous on R2 but not uniformly continuous on R2. So you see, take the sequence n, 0 and u and vn as n minus 1 by n comma 0, and the difference is not going to 0. Here the domain is closed but not bounded. So, okay, so there is a Lipschitz condition even on Rn. Lipschitz condition implies uniform continuity. Uniform continuity implies continuity. So if it is, this is Lipschitz continuous, and this root x is Lipschitz uniformly continuous but not Lipschitz continuous. Similarly, there is a Holder continuous. So Holder continuous implies uniform continuity. This is not, root x is not Lipschitz continuous but is Holder continuous. Similarly, if Fn, we have a similar result for Rn. If the function goes to 0 at infinity, then it is going to be uniformly continuous. So function going to 0 meaning is, given epsilon, there is m such that modulus of fx is less than epsilon whenever norm x or the Euclidean distance is more than m. So this is replica of e to Gaussian in 2 dimension. This is fx is y is e to the power minus x square plus y square is uniformly continuous on R2. Similarly, e to the power minus mod x modulus of x plus y, this is also uniformly continuous because it's going to 0 at infinity. From R2 you can go to, quickly will now I quickly just mention those who are in the second year, third year, they can understand little bit. So there, what is this? This is, there is a distance. Instead of the modulus, there is a distance on the non-empty set x and y, and such a function is uniformly continuous. If the distance in x is small, then the distance in fx and fy is also small. So all those which properties which were there on R or R2, one can do it in metric spaces. So if f is uniformly continuous, then f is continuous at each point. F is uniformly continuous then on x, then it is uniformly continuous on A. So another way to look at it is you define the diameter, and the diameter is smaller. Diameter of E is less than delta, then diameter of f of E is less than epsilon. So as in the case of the Rn, f is not uniformly continuous. You create a 2 sequences so that the distance is going to 0 and the distance is of the images is greater than or equal to epsilon naught. So here is k is compact, then of course every continuous function is going to be uniformly continuous. We have examples of E is subset of R is bounded but not closed, then there is a continuous function which is not uniformly continuous. On the other hand, if Z is the set of integers, has discrete metric, then everything is uniformly continuous. And of course, Cauchy sequence goes to Cauchy sequence in case of this. I can avoid totally bounded, and those who are not interested. We can have more structures in mathematics. These are called topological vector space. So Rn and R are all topological vector space, and any linear map turns out to be uniformly continuous. So those who are in the fourth year can understand some. These are called normed spaces. Normed spaces are automatically topological vector spaces. So any continuous linear map is going to be uniformly continuous, and any uniformly continuous, if you have a topological group, then any continuous function which vanish at infinity is going to be uniformly continuous. That is, it's some kind of generalization of the fact that if the function vanishes at infinity and minus infinity, then the continuous function is going to be uniformly continuous. So there are some structure. These are some COVID. This is bacteria curve where you can find it is at infinity going to 0. So it is a uniformly continuous function. And these are some COVID curves, and finally going to 0. So all of them are uniformly continuous function. And I stop here. You are free to ask me anything. I think I have not taken much time. It is perfectly all right.
If anybody has any query, please raise.
You are free to ask anything. Yeah, only thing I should be able to hear you, or I can come down. Hurry up if you have any question. Nothing. Fine.
No one has. Anyone?
Yeah.
Close
Yes.
in सर हिंदी में तो
हाँ बोलो
सर हम जब क्या नाम है क्लोज इंटरवल बाउंडेड पे जब सीक्वेंस को फॉलो करते हैं तो
क्लोज इंटरवल पे तो अपने आप यूनिफॉर्मली कंटिन्यूअस आ जाएगा,
बट अनबाउंडेड पे वो एक्स टेंड टू इन्फिनिटी जाता है तो उसकी
इन्फिनिटी पे जाएगा. अगर 0 पे जा रहा है तब तो वो यूनिफॉर्मली कंटिन्यूअस हो जाएगा, अदरवाइज नॉट.
पर सर अनबाउंडेड के केस में कई बार होता है कि हमें नहीं होता, मतलब कई बार चैलेंजेस होते हैं कई सारी चीज़ों में, तो उसमें कैसे दिक्कत, मतलब जो फंक्शन है कई बार चैलेंज अनबाउंडेड पे हमें सही डेल्टा या कुछ उसके नहीं मिल पाती, तो उसमें कैसे मतलब
these are from that's why I have given so many criteria. जितने क्राइटेरिया मैंने लिखे थे उनमें से अप्लाई कर सकते हैं. और हमें अभी भी कोई तुम नई सफिशिएंट कंडीशन दे दोगे तो आई विल बी हैप्पी टू सी इट. एनीवन who can give me some
fx is equal to e की पावर x.
ये यूनिफॉर्मली कंटिन्यूअस नहीं है.
सर इसमें क्या डिफिकल्टी, मतलब क्या
because function grow कर रहा है, e to the power x keep on growing
करता रहता है. सर कई बार होता है ये सब ज्यादातर फंक्शन हम ज्यादातर इलेक्ट्रिसिटी वाले जो
तो इलेक्ट्रिसिटी का जो फंक्शन है वो इसका इलेक्ट्रिसिटी लाइफ स्पैन जो है it will go down. Passage of originally when you buy electric apparatus, it has the maximum light and then it keeps on going down to 0. Someday it will be 0. Everyone will be 0. So everything is uniformly continuous. Okay. Hurry up.
Anybody else?
It is a challenging job to find sufficient conditions for a function to be uniformly continuous if the interval is an infinite interval. Not AB, not closed interval AB, not open interval AB, but A to infinity or minus infinity to infinity, both sides. Still we do not know any new sufficient condition is welcome. Yes, nothing more? Okay, fine, thank you.
ये हमारे सर रहे हैं MSc में, and he is that kind of professor who can teach you mathematics without chalk and board. He's a very renowned mathematician. आप जहां से भी बेस से शुरू करो टॉप लेवल तक, आप इट वाज अ रियली अ ग्रेट अपॉर्चुनिटी फॉर यू पीपल. ऐसी बात नहीं है, आप आगे भी एमएससी सब में भी जाओगे तो सर मिलते रहेंगे.
Thank you very much. Thanks for listening. Yeah, thank you. Is it fine?
Yes, it was
It's over?
very good, sir.
No, no. That's,
Thank you so much, sir, for an illuminating and conceptually enriching presentation. I would now request.
एक मिनट बच्चे
Yes.
रास्ता दे दो.
I would now like to request faculty members and guests to move to the extended staff room for lunch. All the students are requested to collect their coupons as they go, and the second coupon will be given at 5 o'clock. And all of you reassemble for the next session at 3:30. Yeah, please stand up for a group photo.